Welcome to the Deep Dive, your shortcut to being truly well-informed. Today we're plunging into a fascinating and incredibly timely topic. We're looking at how two wildly different animal families, the desert-defying camels and the familiar, forest-dwelling deer, manage their body temperatures. More than that, we're going to uncover what their unique evolutionary histories mean for their very survival in a world that's rapidly getting warmer. We've pulled together some pretty in-depth research to bring you the most important nuggets, really. So get ready to unpack the incredible physiological quirks and surprising vulnerabilities of these animals. We'll understand why, for some, adapting to heat is this sophisticated tool they wield, while for others it's a clear sign of a system pushed to its breaking point.
Yeah, our mission today is to go beyond just what happens when an animal gets hot. We want to peel back the layers, really delve into the intricate mechanisms of thermoregulation. We'll explore the clinical consequences when those systems get overwhelmed. And finally, look at the profound and often quite different impacts that climate change is having on these distinct mammalian families. It's a compelling look at how these ancient evolutionary legacies are actively shaping the future of life on Earth, really.
All right, let's start by quickly laying some universal groundwork. You know that feeling when your body just has to be a certain temperature to function? Well, every mammal, including us, needs to maintain a remarkably stable internal temperature. We call this homeostasis, right? And specifically for temperature, it's homeothermy. But why is this stability so absolutely vital for survival?
Well, it's because every single cellular function, every enzyme reaction in our bodies operates within a really narrow optimal temperature range. Step outside that range, and those crucial processes start to break down. Think of it like a finely tuned engine, too hot or too cold, and it just won't run efficiently, or sometimes not at all.
Okay. And central to this homeothermy idea is something called the thermoneutral zone, or TNZ. You can think of this as an animal's Goldilocks zone, the just right comfort zone of ambient temperatures. What happens within that zone? What makes it so comfortable?
Within the TNZ, an animal that's just resting can maintain its core body temperature without expending any extra metabolic energy. It's perfectly balanced. The heat its body naturally produces from just basic metabolism is precisely offset by the heat it loses to the environment. So energy expenditure is at its absolute minimum. What's really fascinating, though, is that this TNZ isn't fixed. It's incredibly dynamic.
It moves.
Yeah, it shifts based on the animal species, its age, health, and really crucially, its coat. Insulation, basically. A white-tailed deer, for instance, has a much wider TNZ in winter because its dense fur provides amazing insulation, helps it stay warm without burning extra calories. This zone is bounded by lower and upper critical temperatures. Those are the thresholds where the animal must start spending energy for active thermoregulation.
Got it. So once you step outside that comfort zone, your body has to work harder,
Right.
and there's a clear hierarchy, you said, behavioral first, then autonomic. Why that order?
Behavioral responses are always the first line of defense, and for good reason. They're energetically cheap. These are conscious actions, things the animal chooses to do to change its immediate environment and reduce the need for, metabolically expensive physiological work.
Yeah.
Imagine a deer seeking out dense shade, or changing its posture to minimize sun exposure, or simply lying down and cutting back activity.
So finding shade actually saves energy it would otherwise spend panting.
Precisely. That deer is actively conserving energy, which is why things like lethargy, seeking shade, or even a reduced appetite are often the very first clinical signs of heat stress you'll see. It's just the animal managing its energy budget wisely.
And when those simple behavioral fixes aren't enough, then the body kicks in with its own internal involuntary adjustments, the autonomic responses.
Exactly. Those are things like peripheral vasodilation, sending more blood to the skin to dump heat, or evaporative cooling through sweating or panting. Very effective, but they cost a lot metabolically.
And regardless of the strategy, heat transfer always happens through those four fundamental mechanisms: radiation, conduction, convection, and evaporation. Right.
That's correct. And crucially, when the ambient temperature actually gets higher than the animal's body temperature, evaporation, sweating, panting becomes the most effective way to cool down. That phase change pulls a huge amount of heat energy away.
Okay, so we've got these core principles. Now let's dive into how two very different groups, camels and deer, have evolved utterly unique ways to deal with heat. Some are, frankly, mind-blowing. Let's start with the Camelidae, a family showing this remarkable evolutionary split. Desert specialists on one side, high-altitude, cold-adapted cousins on the other. The dromedary and Bactrian camels, the desert specialists, are true masters of heat and aridity. Their bodies are just marvels. Take their thick, shaggy fur. You'd think fur would make them hotter, wouldn't you? It seems so counterintuitive.
It really does. But it's the ultimate paradoxical heat shield. That thick fur isn't trapping body heat, it's insulating them from the intense solar radiation and the scorching air, minimizing heat gain from outside. Think about this. A shorn camel, one without its natural insulation, needs a staggering 50% more water to sweat just to avoid overheating.
50% more. Wow.
Yeah. That single fact just flips our whole understanding, doesn't it? It reveals the fur not as a heat trap, but as the sophisticated water-saving heat shield. Truly paradoxical. And the sweat they do produce evaporates right at the skin level using body heat for cooling, while the fur's outer surface stays dry, preserving its insulating power.
Amazing. Does that mean we've kind of gotten it wrong about fur and heat for other animals too? What other anatomical tricks do camels have?
Well, their long legs aren't just for walking. They lift their bodies higher off the scorching desert floor, which, can hit 70 degrees Celsius.
70 C. That's incredible.
It is. And when they lie down, they have this thick pad on their sternum, the sternal pedestal, which props their body up, letting cooling air circulate underneath. And unlike most mammals, their fat is concentrated in their humps, not spread out under the skin. This actually helps heat dissipate from the rest of their body.
But the physical stuff is just the start. What's going on inside?
Oh, yeah.
I've heard about adaptive heterothermy. That sounds like a seriously complex internal trick.
It is, and it's absolutely key to their survival where water is scarce. When water's limited, a camel deliberately allows its core body temperature to fluctuate widely. It can drop to around 34 Celsius at dawn, and then climb to 41 C or even more in the late afternoon.
So it's not a fever, it's a strategy.
Exactly. It's not a failure of regulation, it's a brilliant water-saving strategy. They effectively store daytime heat, then passively radiate it away into the cooler night air without spending water on cooling. Plus, by letting their body temp rise closer to the ambient temp, they reduce the difference, which minimizes more heat gain from the environment. It's incredibly clever.
And their ability to manage water is just
Good.
legendary, tolerating dehydration that would kill almost anything else. How did they do that?
It's a whole arsenal of adaptations.
Yeah.
First, their kidneys produce incredibly concentrated urine, and their feces are almost bone dry. Every drop is conserved. But there's even more, right down at the cellular level.
Cellular level, you mean like their blood itself?
Yeah.
Precisely. Their red blood cells are oval-shaped, not round like ours. This isn't just some quirky detail, it's critical. This shape lets their blood flow easily even when it gets really thick during severe dehydration. And here's the kicker. When they finally find water, they can drink over 100 liters in minutes.
100 liters, yep.
And those oval cells are flexible enough that they don't burst from the sudden osmotic change. This also helps keep their plasma volume stable, maintaining circulation even when they're severely dehydrated.
And they even protect their brain, specifically, when their core temp is soaring.
Yes. The rete mirabile. It's a special network of arteries and veins at the base of the brain. It uses a countercurrent blood flow system to cool the arterial blood going to the brain. This ingenious setup protects it from heat damage, ensuring brain function even when the body's pushing past 40 C. And when they do need evaporative cooling, they rely almost entirely on economical sweating. They don't really pant much for thermoregulation.
Beyond all that internal magic, they also use some pretty smart behaviors, right?
Simple, but effective. They'll orient their bodies to minimize sun exposure, reducing the surface area hit by direct sun. They rest during the hottest parts of the day. And a lesser-known one. If the air temp is hotter than their body, they might even huddle together.
Huddle. Wouldn't that make them hotter?
You'd think so, but it actually reduces the collective surface area exposed to the even hotter environment, minimizing heat gain for the group. Clever stuff. Now, if desert camels are the masters of heat, their South American cousins, llamas and alpacas are, well, completely different. They're optimized for the cool, high Andes, and their main adaptation for that cold place becomes their biggest problem in the heat.
Their fleece?
Exactly. Their thick, dense, insulating fleece, which is fantastic in the cold, becomes a disastrous heat trap in warmer climates. They just can't shed heat effectively across their whole body. Instead, they rely on small, sparsely fleeced areas called thermal windows, mostly on their belly, underarms, inner thighs. These make up maybe only 20% of their total skin surface.
Wow, so their entire cooling strategy relies on these tiny windows. That explains why people talk about precision cooling for them, targeting those spots. Makes sense.
It does, and what's really striking is that domestication, breeding them for that super valuable fiber, might have accidentally made them more vulnerable.
How so?
Well, wild lemoids have a double coat, but Domesticated alpacas have been selected for an extremely fine and dense single coat. It's a classic trade-off. We got better fiber, but at the cost of their heat tolerance.
But they do still try to cope, right?
Yeah.
Even if they get overwhelmed easily.
Oh, absolutely. They will cush, that's their term for lying down sternally to press their undersides against cool ground. They instinctively seek breezes, and they'll readily wade into pools to cool those thermal windows. They do have some daily temperature fluctuation, but nothing like the extreme adaptive heterothermy of desert camels. Their sweating and increased breathing just get overwhelmed quickly, especially if it's humid or they haven't been shorn, which is exactly why tools like the Heat Stress Index, HSI, are so vital for owners. An HSI over 150 means risk, and over 180 is high risk for llamas and alpacas. You need to watch them closely.
Okay, let's shift gears entirely now to the deer family, Cervidae. Found all over temperate and boreal zones, their strategies are tuned more to seasons than constant extreme heat. Physiologically, they have a much narrower thermoneutral zone than camelids, don't they?
Much narrower. For example, a white-tailed deer's upper critical temperature is around 68 Fahrenheit, or 20 Celsius. Compare that to a moose, a real cold specialist, which can start showing heat stress signs as low as 57 F or 14 C.
That low? Wow.
Yeah, it really shows their low physiological tolerance for heat. Their most critical physiological adaptation is their pelage, their coat. It's thin and reddish in summer for heat loss, then dense and insulating in winter. But this seasonal change is a double-edged sword. It means they're incredibly vulnerable to unseasonal heat waves, like a surprise hot spell in spring when they're still wearing their winter coat.
And for cooling, most deer rely mainly on panting. Rapid, shallow breathing.
That's right, dissipating heat from the respiratory tract. But this brings up a critical point. What's the downside to panting, especially compared to, say, the camel's sweating?
Okay, what is it?
Well, unlike economical sweating, excessive panting can lead to respiratory alkalosis. They blow off too much CO2. This, in turn, can mess with the buffering capacity of their rumen.
The rumen, their stomach.
Exactly, part of their digestive system. It significantly increases the risk of ruminal acidosis, which is a serious metabolic disorder. It's worth noting, though, elk are a bit different. They mostly sweat.
So for deer, like most mammals, behavior is the first preferred defense. Their survival in hot periods seems totally tied to their habitat quality.
Completely. The #1 strategy is seeking thermal refugia. Deer actively look for cooler microclimates. We're talking dense forest canopies, north-facing slopes that get less sun, cool creek bottoms with shade, moving air, maybe water. Research clearly shows they strongly prefer areas with really good shade, like 90% canopy cover once temps get over about 85 F. This just hammers home how habitat degradation removing those refuges can turn a manageable heat event into a lethal one. It strips them of their best coping tool.
And to further cut their heat load, they change their activity patterns too.
Definitely. They move less during the hardest parts of the day, shifting foraging to cooler times like dawn, dusk, or even nighttime. And they also tend to reduce how much they eat.
Eating less. Why?
It's adaptive. Digesting food actually produces metabolic heat, so eating less minimizes that internal heat source.
But wait, here's where it gets really tricky, isn't it? Reducing feeding creates that critical nutritional bottleneck. Summer is vital for deer. Does are lactating, fawns are growing like crazy, bucks are growing antlers. All that takes huge amounts of energy and protein.
Exactly. Heat stress forces this direct conflict. The physiological need to eat less clashes with the immense demand for nutrients. This often leads straight into a negative energy balance. It impacts calf growth, milk production, body condition going into winter. It has knock-on effects for survival, future reproduction, the whole population dynamic. It's a serious catch-22.
Right.
So if we connect all these pieces, looking at the big picture, the comparison shows these fundamentally different evolutionary paths to solving the heat problem. Totally reflects their different ancestral homes. Think about core body temperature control. Desert camels use adaptive heterothermy as a proactive water-saving tool. A fluctuating core temp for them signals an efficient system.
Right, it's supposed to do that.
Exactly. But Cervidae, they're strict homeotherms. A significant rise in their core temp is not a stratagem. It's a sign their defenses are failing. It's pathology.
And the South American camelids are stuck in the middle. Some ancestral wiggle room, but the fleece makes it dangerous.
Precisely. They have some of that ancestral heterothermic ability, but their thick fleece, evolved for cold, turns it into a liability. It predisposes them to uncontrolled overheating.
Okay, and the cooling mechanisms.
Desert camels. Economical sweating, no problematic panting. Cervidae, mostly panting, with potential issues like acidosis. Elk being the exception, mostly sweating. South American camelids use a mixed sweating from thermal windows plus increased breathing.
And water economy. Big difference there.
Huge. Desert camels evolved around water independence, extreme conservation, cervidae. No extreme internal tricks. They absolutely depend on finding and drinking free water. And finally, the coat itself plays functionally opposite roles. For desert camels, fur is a heat shield, insulating them from heat.
Well, for the others.
For South American camelids and cervidae, the coat, or fleece, is an insulator against cold. It's part of their heating system. In hot weather, that insulation becomes a major liability, trapping body heat.
So what does this all mean when things go wrong? When an animal's defenses are just overwhelmed, we see the clinical signs, the pathology. It seems clearest in South American camelids because we manage them outside their native range. What are the early warning signs?
Often the first signs are behavioral and fairly subtle. You might see lethargy, maybe they seem depressed, off their food, nostrils flared, unwilling to move or get up if they're cushed down. You also likely see an increased breathing rate, maybe over 40 breaths per minute, and a faster heart rate, over 90 beats per minute.
And if it gets worse, what are the more severe signs?
Things get more alarming. Open-mouthed breathing, drooling or foaming, a drooping lower lip, obvious weakness and trembling. In intact males, you might see scrotal swelling. Eventually, they might not be able to stand and can collapse. A rectal temperature over 104 Fahrenheit, that's 40 Celsius, is a clear sign of serious hyperthermia.
You mentioned a key study on 15 heat-stressed camelids. What did that reveal physiologically? What's happening inside?
Some really stark things. Severe myonecrosis, basically muscle tissue breaking down. You see sky-high muscle enzymes in their blood. Also, hypoalbuminemia, which was a novel, finding low protein in the blood, which actually contributes to fluid retention and swelling, kind of the opposite of what you might expect with dehydration.
That is unexpected.
And quite surprisingly, a decreased packed cell volume, suggesting fluid shifted out of the blood vessels. They even found mild spinal axonal degeneration, subtle nerve damage in the spinal cord, which likely explains that progressive weakness and inability to stand you see in severe cases.
Even the super resilient desert camels aren't totally immune, though. Prolonged drought and heat must take a toll.
Absolutely. They're survival masters, but prolonged drought plus extreme heat still leads to severe malnutrition, drops in milk production, and makes them more susceptible to diseases. Blood tests might show higher packed cell volume, hemoglobin, protein, glucose, liver enzymes, all signs of systemic stress.
And in deer, wild or farmed, what are the first clues they're struggling?
Behavior changes are earliest and most obvious. A clear drop in movement, more time lying down, shifting habitat use right into any available shade and water. As the stress gets worse, you see the physiological signs. Excessive panting, drooling, severe cases. Weakness, they might look dazed or uncoordinated, and then collapse.
And the underlying issues in deer sound like a complex breakdown.
It really is. You get endocrine disruption, the stress response kicks in, cortisol surges, which over time can suppress metabolism and immunity. Then there's that negative energy balance we talked about, eating less while spending more energy trying to cool down. That directly hits growth, lactation, antler development.
Plus the rumen acidosis risk and panting.
Yes. Panting causes respiratory alkalosis from CO2 loss, and drooling means less saliva buffer reaching the rumen. It's a recipe for digestive upset. And finally, all this chronic stress and poor nutrition leads to immune suppression, makes them much more vulnerable to parasites and diseases. So given these very specific vulnerabilities, it's clear management has to be tailored. For South American camelids managed outside the Andes, preventing heat stress is, well, it's not optional. It needs intensive, proactive work.
Environmental modification is key then. What does that actually involve?
You need plenty of shade, big enough for the whole group. Good ventilation is critical. Large barn fans positioned to blow air across the animals at floor level, targeting those ventral thermal windows. Constant cool drinking water, obviously, but also shallow wading pools. Kiddie pools work well, kept clean and shaded. They really help. Misting or sprinkler systems, ideally with fans for evaporation, are also great.
And husbandry. I know shearing is huge for them.
It's the single most important thing before hot weather hits. Removing that dense fleece is night and day for their ability to cool off. But here's a massive caution. You must never just hose down a fully fleeced, heat-stressed alpaca or llama.
Why not? Seems intuitive to cool them with water.
Because the fleece traps the water against the skin, it heats up fast, effectively cooking the animal. It makes the hyperthermia worse. Housing should only be done on shorn animals or targeted right onto those thermal windows and legs.
Okay, critical point. What else? Bedding.
Avoid straw in summer, it insulates. Use cool surfaces like sand, pea gravel, or concrete if possible.
Panhandling.
Keep it to a minimum and always schedule non-essential stuff like transport for the coolest part of the day, early morning usually. Nutritionally, adjust feeding times to early morning, late evening, reduce that digestive heat load during peak heat, and maybe offer electrolytes in a separate water source. Now, for cervids, wild or farmed, the approach depends on the setting. For wild populations, habitat management is everything. The goal is maintaining and creating thermal refuges. This means landscape conservation. Preserving mature forest canopies for deep shade, protecting north-facing slopes, conserving riparian corridors, creek bottoms with shade, water, air movement. You can even actively manage for shrubby plants like sumac that create good umbrella shade. And ensuring widespread water access is absolutely vital.
For farmed deer, you can do more direct things, I guess.
Right. Artificial shade structures are important.
Yeah.
Sprinkler systems can work well. And providing high-quality supplemental feed is key to counteract that negative energy balance from heat stress. And just like with camelids, any handling, processing, transport, move it to the cooler morning hours. Don't add handling stress on top of heat stress.
Which brings us to the really big question. How will these deep-seated differences play out in a warming world? Let's start with the Camelidae and climate change.
For South American camelids, especially those outside the Andes and temperate zones, the future looks tough. A significant increase in heat stress is likely. Their cold adaptations just make them fundamentally poorly suited for hotter, more humid summers. Their welfare, even their presence in these areas, will increasingly depend on intensive, energy-guzzling human management, mandatory shearing, cooling systems. It's a big commitment.
So, managed survival for them. What about the desert camels? Resilient, yes, but surely not immune.
No, not immune. More frequent, intense droughts threaten their food and water, leading to malnutrition, disease. But here's the paradox. Their very resilience is leading people to promote them as a sustainable, low-input alternative to thirstier livestock like cattle in arid lands.
So they might be part of the solution for us, even as they face challenges themselves.
It's looking that way, potentially. A fascinating twist.
Now, for Cervidae, climate change sounds like a really mixed bag. That winter benefit versus summer detriment idea?
Exactly. Milder winters, generally good. Less cold mortality, maybe some northward range expansion. But that benefit is being swamped by hotter, drier summers, which are set to exceed their physiological limits more often. This has real population consequences. We're already seeing range shifts, heat-sensitive moose declining down south.
Right.
That chronic nutritional bottleneck from summer heat. It's predicted to lead to lower fitness, smaller average body size, reduced reproductive success. And on top of that, warmer weather expands the range in active season for nasty parasites like winter ticks and brainworm and disease vectors for things like EHD, so more disease pressure.
Can they adapt behaviorally, like shifting to night foraging?
They do show behavioral plasticity, yes, but those adaptations have limits. Behavior can't fully compensate for widespread habitat loss or the direct physiological cost of chronic heat. Models that don't account for both behavior and its limits might be underestimating how vulnerable they really are. What's really interesting here is what you might call a management inversion emerging. For camelids, it means intensifying management for vulnerable SCs, treating them like sensitive livestock, while potentially leveraging desert camels as resilient, low-input animals in dry areas, almost climate-adapted livestock.
For deer.
A totally different game. Managing a wild species hitting its limits across huge ecosystems. That needs broad habitat-level interventions. It's vastly more complex than managing a herd. So, in essence, the desert camel, with its incredible water independence, adaptive heterothermy, that paradoxical fur heat shield, it represents one masterful evolutionary solution to extreme heat. Cervids, on the other hand, rely mainly on energetically driven behavioral avoidance, a strategy totally dependent on having those thermal refuges in their habitat. And caught in the middle are the South American camelids, whose specialization for cold, high places leaves them acutely, tragically vulnerable to heat stress.
Yeah, what really stands out is just how profound these deep-seated physiological differences are, and how directly they're going to dictate the health distribution, maybe even the survival of these animals as temperatures keep rising. Understanding this comparative biology isn't just, academic. It's absolutely essential for effective conservation, sustainable husbandry, building robust predictions for the future. So as you go about your day, maybe think about this. The future fates of these two remarkable families, shaped by evolutionary legacies laid down long ago, will be a direct and pretty telling reflection of our changing world. What other animal adaptations, maybe hidden in plain sight, might reveal surprising vulnerabilities or perhaps incredible resilience as the climate continues to shift. Something to ponder on your next walk.